Okay, now we want to talk about angle measure. And intuitively we say, the wider this thing is, the opening, the bigger the angle is. So it makes sense. So how do we go about doing that? Well, what we really want to do is to move out 1 unit distance here, follow a path of an arc from between the 2 points here. And so we want to measure this red distance. Intuitively we can think about taking our ruler and just wrapping it around this circle, our tape measure, and measuring that arc length. Unfortunately, we haven't formally talked about measuring any kind of an arc length, so we need to come up with another way to do this. Well, one possible way to do this is we have talked about the length of a line segment, so we could talk about the line segment between these 2 points here and talk about its length, and then make, basically get the red length from the red arc length as a function of the black length here. And so there's a way to do that, and what it really involves is an arc sine function. Well, we haven't even talked about, it's way too early for us to be talking about a sine function, much less an arc sine function. But we do assume we know about real numbers, and real numbers, of course, are sequences of what we call Cauchy sequences or convergence sequences of rational numbers. And so for that to make sense, we have to know what we mean by a sequence to converge. And we could use a standard Maclaurin series for our arc sine to come up with a formal definition. And so it would be like this here, this summation here, and it would be based on the length x of this here. Notice it goes from 0 at a 0 angle up to a straight angle. It's a length of 2. So this line segment would go from 0 to 2, and the arc length then would end up going from 0 to pi. And that would be accomplished by this. So we could formally do it this way. So in fact, we don't necessarily have to postulate the existence of an angle measure. We could actually define it in terms of some things that we've done before. However, this is not really nice in the sense that it requires a lot of machinery that, we probably haven't, well, you guys have seen it because you've done it in, you've all had at least Calculus 2, but, this is not kind of thing you could do with a high school class by any means. So what we're going to do is we're not going to use this definition, so you don't have to know that. What we're going to do instead is actually just postulate the existence of an angle measure with certain properties. And we're going to approach things that way. But in fact, we could define angle measure as I just said, and then we could prove these things as theorems, although it might be a little bit difficult to do. But we're going to postulate the existence of this. Now, what you do need to know is this informal way of thinking of angle measurement. That is very important. But this part here, this formula and so forth, don't worry about that. Okay, so here's what we're going to do formally then. We're going to have our 12th postulate that says there exists an angle measure function which maps a set of angles onto the interval, that should be the interval 0 to pi, closed interval, 0 to pi, of the real numbers. We call the output of this function applied to angle ABC as the measure of angle ABC and denoted as m ABC. Furthermore, this function is subject to the following conditions. The measure of an angle is 0 if and only if it's a 0 angle. The measure of an angle is pi if and only if it's a straight angle. And then we have the protractor postulate. Given any ray in the edge of a half plane and a real number x, there's a unique ray in the closed half plane such that the measure is a particular given number, x, okay, and a real number x, and a real number x in the interval 0 to pi. There exists a unique ray in the closed half plane such that the measure is x. Conversely, given any ray in the closed half plane, there exists a real number x such that the measure equals x. And I could also say in that interval, because that's where our measures are. Okay? And then we have the angle addition postulate. D is a point in the interior of ABC if and only if the measures angles of these angles add up. So let's sort of say, so here we're saying, the first part says, if we have an angle here and we're talking about just the half plane up here, then give me the measure and then I can make exactly one angle that has that measurement. Or if you give me that ray, there's exactly one measure that ray has, that angle has. Okay? And as far as the interior part, we say that this one here, the red one, is interior to is an interior ray. The point D is in the interior. Let's say. Let's give this some things. This is AB. A, B, and then C. Okay, so that would be the labeling that goes with the first part up here. And then if we pick a point D in the interior, then if D's in the interior, then we measure this angle DAC and the angle BAD, and that has to add up to the measure of angle BAC. If D's in the interior. If D's not in the interior, then that's not true. You can clearly see that BAD plus CAD is definitely larger than BAC. Okay? And of course it goes the other way around. It's an if and only if. So if those measurements add up, then D has to be in the interior. We'd say that D's in the interior, and then we say that this ray AD is between rays AB and AC. So there's a betweenness for rays. And you know what? Let me go ahead and AD is between AB and AC. So it'll match the picture. Okay, so the same picture matches there. We say two angles are congruent angles if and only if they have the same measure. Two lines that intersect to form congruent angles are called perpendicular lines. So notice one of the things that we noticed, and we can actually prove, is that if two lines intersect, that we have four angles formed here. But we only really have two sizes, okay? But if we can get all four of them to be the same size, so vertical angles are congruent, which was, did we get that as a theorem up here? Okay, it'll be a theorem down below, okay? But if we get it to where all four angles are congruent, we call those perpendicular lines. Okay, some other things that we can define here. The congruent angles are formed by perpendicular lines are called right angles. More generally, two subsets of a line, say line segments or rays, are perpendicular if the lines containing them are perpendicular, even if those two things don't actually meet themselves. An acute angle is an angle whose measure is more than 0 but less than the measure of a right angle. Obtuse angle is an angle whose measure is more than the measure of a right angle but less than the measure of a straight angle. The degree measure of an angle is the radian measure of an angle multiplied by 180 over pi. We use a symbol, a little raised circle, to denote degrees. So 180 degrees equals pi. So notice that the degree symbol is not present. It's assumed that the standard radian measurement is intended. Okay? If you don't see a degree symbol, you mean radians. Radians is the better way to do angle measurement. Okay, so if you have the degrees are a more ancient system from ancient Babylon, and so we prefer to use radian measure, and we'll use radian measure when we're doing formally anything formally in this class. So two angles are supplementary angles if and only if the sum of their measures equals the measure of a straight angle. Two angles are complementary if and only if their measures equals the measure of a right angle. then we talk about supplements and complements. So then from that, those definitions, we can prove the actual measurements here of the angles. So notice that basically, just as the ruler postulate let us develop the ruler to measure distances, the angle measure postulate allows us the ability to take a curved ruler to measure distances, which is essentially a protractor. So a Euclidean protractor is just a segment of a number line running on the interval -1 to 1 with along a semicircle or radius 1 centered at the origin of that line. Let me just say bent. So we think of that informally that way. So we have some other propositions. Congruence of angles is an equivalence relation. Two angles forming a linear pair have measures that sum to pi. If a pair of complementary angles are complementary, they're both acute angles. If two angles are both supplementary and congruent, they're both right angles. Supplements of congruent angles are congruent. Complements of congruent angles are congruent, and vertical angles are congruent. So that's a basic proposition or several propositions about angles that are put together. Sometimes this is really several different propositions really, but if they share a common theme, sometimes I'll group those together in one proposition with various parts. A definition of bisector of a proper angle. ABC is a ray BD, and the interior of ABC such that the measure of ABD and the measure of DBA is the same. A zero angle is its own bisector. A bisector of a straight angle is a ray perpendicular to a straight angle with endpoint at the vertex of the straight angle. Every non-straight angle has exactly one bisector. A straight angle has exactly two bisectors which form a straight angle themselves. Proposition 30, given an angle, an array, and a half plane H with the edge the same as the ray, then there exists exactly one ray such that D is in the half plane and is congruent to the given angle. Proposition 31, given C and D on opposite sides of a line, then the intersection of AC and ray BD is the empty set. It will not cross there. Given that B is between A and C and E and D are points on the same side of line AB, then BD intersects either line segment EC or EA. Okay. And the Crossbar Theorem, if the endpoint of a ray is at the vertex of an angle and the ray contains a point in the interior of the angle, the ray intersects every segment whose endpoints are on the angle but not on the same ray of the angle. Let's look at this one a little bit. So we've got a line AB. Okay. Okay, so we got ourselves a line AB, and C and D on opposite sides. Let me go ahead and do this. The line segment. Oops, I think I made a ray there. Then, let's see, C and D are opposite sides of AB, and we look at segment AC, which is right here, and we want to look at, let's give it a different color, make it green. So segment AC, and we want to compare that to ray BD. Which is, let's give it a color, how about, black. Okay, so the black, we're looking at the black versus the green. If D is on this side, there's no way it's going to intersect the line segment that's over here. That's part A. Again, this is a Euclidean illustration. You'll need to show that this works in the other geometries. we'll need to pay special attention to spherical to make sure I didn't slip up on something there. Okay. So that's the part A illustration. So let me make an action hide button for that. Oh, that's not what I want. Okay, I'll name that. I'll fix that in a minute. Now the next one is ABC. So again, let's do a line here, and I'll do a line segment here, and we'll put a point B in the middle of that segment. So we have A on this end, we have B on this end. Now we have B in the middle, right? Yeah, we have C on this end. B's in the middle. B is between A and C. Okay. E and D are on the same side of the line. So now we got points over here. E and a point D. D and E on the same side. Then we look at ray BD. And then we look at the line segments. Here and here. And we're saying the black ray has to intersect one of the green sides, including maybe this point here. Or one of the 2 points here too. So C's on this same side as E. It's got to go through here or here. Again, we've talked about it. This is a Euclidean illustration. It doesn't matter where these points are. Okay, so there's the Euclidean illustration of what's going on for that part. And the crossbar theorem, let's see, if the end point of a ray is at the vertex of an angle, okay, let's make us an angle. We'll make another ray. Okay, so we got our green angle. And then we have a line segment going from one side to the other here. So let's make that black. We'll make this part right here red. Okay, so what we're saying is that the red thing is going to have to intersect the black segment here, no matter where it is, as long as it's in the interior. If it's in the exterior, it doesn't say anything about it. It doesn't matter what size the angle is. That's the crossbar theorem. Okay, so some of these proofs may be for homework problems, others we may prove later, but at least we want to get through the statement of all these theorems right now at this point. And those are the basic formal things we're going to be doing this week. Now informally we're going to be looking at, in the tasks, what an angle looks like in each of the different geometries. Okay, and the nice thing about the angles that we have here in our models that we're going to be using is once you understand what's going on with Euclidean angles, first of all, angles in taxicab geometry are exactly the same objects as they are in Euclidean geometry, and they're measured exactly the same way. So that's good. In hyperbolic geometry, angles are measured the same way you would measure two curves, the angle between two curves in Euclidean geometry, and that is the angle between their tangent line, Euclidean tangent lines. And then in spherical geometry, kind of the same thing. We look at the angle between the Euclidean tangent lines to those circles, great circles on the sphere, and that's going to be how we measure them. So we say that those models, the spherical geometry, the taxicab, and the hyperbolic model, if it's the hyperbolic half-plane model, those are conformal models, and that just means that the angle are measured essentially the same way as they would be measured in Euclidean geometry.